Math Lead learners! Welcome to Mathematics Lead channel, where we turn your math worry into mastery. I am teacher Jamie Rosales and together, let us have fun while learning. For today's discussion, we're going to prove the remainder theorem, factor theorem, and rational root theorem. For our learning objectives, at the end of the lesson, the student should be able to state, explain, and prove the remainder theorem using polynomial long division, state, explain, and prove the factor theorem using the remainder theorem, and state and explain the rational root theorem. But first, we're going to have our engaging activity. Today, we're going to play a fun word game which is the Scramble Scramble. I prepared a set of scramble words and your task is to unscramble the words. Are you guys ready? Ready. And the first scramble, and you got it right, remainder. And our next scramble, correct, factor. This scramble is, yes, polynomial. Next scramble, very good, theorem. What do you think this scramble? Yes, root. How about this scramble? Excellent. Correct. It's proof. And for our last scramble, correct. It's rational. Great job. Thank you everyone for your cooperation. You all did great in our engaging activity. And to activate your knowledge, let's proceed to our discussion. Okay, let's start with remainder theorem states that when a polynomial p of x is divided by the binomial quantity of x minus a, the remainder obtained is p of a. So this theorem essentially tells us that we can find the remainder of a polynomial division without actually performing the long division. We simply substitute the value of a into the polynomial p of x. So let's try the example. If p of x is equal to x cubed plus 2x squared minus 5x plus 2 divided by binomial x minus 1 is, so the value of x is equal to 1. Therefore, we're going to substitute 1 in all x. We got P of 1 is equal to 1 cubed plus 2 multiplied by 1 squared minus 5 multiplied by 1 plus 2. We got P of 1 is equal to 1 plus 2 minus 5 plus 2 equals 0. So our P of 1 is equal to 0. So next, to prove the remainder theorem using polynomial long division, we have four steps. The first step is divide P of x by x minus a using polynomial long division. And next step is the result will be a quotient q of x and a remainder r. Third step is we're going to write the equation into p of x is equal to quantity of x minus a multiplied by q of x plus r. And for the last step, we are going to substitute x equals a. Therefore, the value of p of a is equal to r. So let's have an example. Find the remainder when p of x is equal to 2x squared plus 5x minus 3 is divided by quantity of x plus 2. So our step 1 is the polynomial long division. We perform polynomial long division of 2x squared plus 5x minus 3 by x plus 2. So we got the remainder of negative 5. For our step 2, identify quotient and remainder. The quotient q of x is 2x plus 1 and the remainder r is equal to negative 5. So for step 3, write the equation. Following the general form, p of x equals to quantity of x minus a multiplied by q of x plus r, where a is equal to negative 2 since we're dividing by x plus 2 equals x minus negative 2, we get p of x equals quantity of x plus 2 multiplied by 2x plus 1 minus 5. So for our last step, substitute x equals a. Our x is negative 2, therefore our a is negative 2. By substitution, p of negative 2 is equal to quantity of negative 2 plus 2 multiplied by the quantity of 2 times negative 2 plus 1 minus 5. We have p of negative 2 is equal to 0 multiplied by negative 3 minus 5. Our p of negative 2 is equal to negative 5. Therefore, the remainder when p of x is equal to 2x squared plus 5x minus 3 is divided by x plus 2 is negative 5. This matches the remainder we found using polynomial long division, demonstrating the remainder theorem. And now let's proceed to the next theorem, which is the factor theorem, which is direct consequence of the remainder theorem. It states that x minus a is a factor of p of x if and only if p of a is equal to 0. In our previous example, since p of 1 is equal to 0, therefore x minus 1 is a factor of p of x since p of a is equal to 0. And to prove the factor theorem using the remainder theorem, we have three steps. The first step is to, if x minus a is a factor of p of x, the remainder when p of x is divided by x minus a is 0. And step 2, by the remainder theorem, we are going to evaluate p of a. And the step 3, which is the last step, is the conclusion. Let's illustrate this with an example. Consider the polynomial p of x is equal to x squared minus 5x plus 6. Let's determine if x minus 2 is a factor. In applying the step 1, apply the factor theorem. If x minus 2 is a factor, then p of 2 should equal to 0 according to the factor theorem. Then step 2, evaluate p of 2, which is you're going to substitute x is equal to 2 into the polynomial. So with that, we have p of 2 is equal to 2 squared minus 5 multiplied by 2 plus 6. It's equal to 4 minus 10 plus 6 equals 0. So for our conclusion, since p of 2 is equal to 2, the factor theorem confirms that x minus 2 is indeed a factor of p of x equals x squared minus 5x plus 6. And now let's proceed to our last topic, which is the rational root theorem. If a polynomial equation with integer coefficients has a rational root, then the root must be of the form of p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. This theorem helps us to find the potential rational roots of a polynomial, and it narrows down the possibilities by considering the factors of the constant term and the leading coefficient. Let's say we have the polynomial equation 2x cubed minus 5x squared plus 3x minus 1 equals 0. The constant term is negative 1, and the p-value or the factors of negative 1 is positive negative 1. And our leading coefficient is 2. Therefore, our q or the factors of 2 is positive negative 1 and positive negative 2. Therefore, the possible rational roots are all the combination of p over q is positive negative 1 and positive negative 1 half. And next example is 2x squared plus x minus 3 is equal to 0. Our constant term is negative 3, and our p-value, which is the factors of negative 3, is positive negative 1 and positive negative 3. The leading coefficients is 2, and our q value is the factors of 2, which is positive negative 1 and positive negative 2. Therefore, the possible rational roots are all the combination of p over q is positive negative 1, positive negative 3, positive negative 1 half, and positive negative 3 halves. And now, to develop your competencies, I prepared some problem that you're going to solve. Answer these following problems and you may type your answer in our chat box. So, thank you for listening. I hope you understand our lesson and gain more knowledge. Again, I am Jamie Rosales. See you in our next video.